Our next stop in our exploration of circles is we're gonna take a detour into looking at chords. Recall yesterday that a chord was simply a segment whose endpoints are on a circle. A chord is simply just a segment whose endpoints are on the edge of a circle, or on a circle. We're going to look at some properties of chords. Our first one is I'm calling the chord arc congruence theorem. It's just numbered in your book, but I don't like numbers for theorems. So I named it the chord arc congruence theorem. It says the following. It says that, what do I say? It says that two minor arcs are congruent if and only if the chords connecting their endpoints are also congruent. Two minor arcs are congruent if and only if the chords connecting their endpoints are congruent. So, for example, given a circle, if I have a circle here and I have, say, arc AB is congruent to arc CD if and only if segment AB is congruent to segment CD. Unless these are congruent, then those arcs themselves won't. Those segments are congruent, those chords are congruent, then those two minor arcs will be congruent. Okay. This symbol, that was a double imply. It implies both ways. This implies this. Same way. It's a logical symbol. So if we know something about the chord lengths here, we can claim something about the minor arcs. Or vice versa, if you know something about the minor arc length, then we can claim something about the length of these segments, these chords that are being drawn in. So if I want to find, say, the measure of arc UT, something I can do is, well, since if I'm looking at the chord, or the segment connecting the two endpoints of this chord, I know that arc SR is 85 degrees. It's measured by its central angle. And I know that this chord is congruent to this chord. So by our theorem, since these two chords are the same measure, then these two arcs are the same measure. So I know from the theorem that arc SR is congruent to arc TU. So if I knew the measure of arc SR, I could find the measure of arc TU. Well, I know the measure of SR. What's the measure of arc SR? 85 is the measure of arc TU. Similarly, arc EG is congruent to arc FG. If EG is length 6, then our theorem forces segment FG to also be 6 as well. Since the arcs are congruent, therefore the chords must be congruent. The 6 and yeah, the congruent symbol is arcs are measured in degrees. So this 6, since it's not in degree, must be implied. That's on this chord. How are we going to find the measure of arc AB in our second example, in our other example? Well, we'll get a ruler. That's not going to help very much. If arc BC is 100, well, I know that these two chords are the same measure. So if these two chords are the same measure, then what else do I know? What else do you know if these chords are the same measure? The arcs are the same measure. So if these arcs are the same measure, then I know, and by the arc addition postulate, I know that arc AB plus arc BC plus arc CA has got to be this whole circle. What's the degree measure of an entire circle? 360. So I know that if I take 360 and I added, and that should be equal to, excuse me, that's equal to 100 plus whatever AB is, plus whatever AC is. And I know these two things are the same by my previous theorem. I know that these two arc measures are the same because these two chords are the same length. So 360 is equal to 100 plus twice of whatever AB is. You can find the measure from AB there. Subtract 100, 260, divided by 2. 260 divided by 2 is 130 degrees. AB is 130, and AC is also 130. All right, let's look at a second situation. It says as follows. I'm going to draw a quick picture down here on the bottom, and we'll talk about what the theorem's going to look like. If I have a circle, and I draw one chord, and then a second chord is a perpendicular bisector of it. So my second chord here is perpendicular and bisects it. Right? You don't have to draw this picture right now. I'll give you some room in a second. If I have my first chord here and then I have another one that is a perpendicular bisector of it, just by like intuition here, what does this second chord look like it is? This looks a lot like a diameter. And in fact, this is what our perpendicular bisector theorem is going to say. Is that if one chord is a perpendicular bisector of another, then this first one here must be a diameter, is our first congruence theorem here. Our first chord bisector theorem says that if one chord is the perpendicular bisector of another chord within the same circle, then the first one must be a diameter. Part 2 is going to be the converse of this. It says that if a diameter is perpendicular to a chord, then it bisects the chord. is the second part of this. They're saying very similar things. So it's just the hypothesis of each of these. The first one says, if I start with two chords, one of which is a perpendicular bisector of the other, then what I can conclude is that that first one must have been a diameter. It has to go through the center of the circle. Vice versa is if I start with a diameter, and I also know that it's perpendicular to some other chord, I know that it must bisect the chord. I must cut that second one, that smaller one, in half. It bisects it. That's the two ideas. And that's what the little drawing I put down here. If you wrote small enough, you could put little drawings in here if you'd like. We're going to see some examples of what this looks like on the backside. Okay. Does everyone have this copy down? Can I flip the screen? So I'm going to use the diagrams and what I know to find some missing variables. So the first one, let's see, I have a circle. I have, well, clearly two chords, and one is perpendicular, and CE happens to be a diameter. It's going through the center of the circle. So if I know that I have a diameter and it's perpendicular to another chord, what do I know about these two the relationship between these two chords? One of the chords is bisecting the other. This diameter is bisecting the other chord, which means that segment congruent to segment. So then, knowing that, what's the length of segment BD?
10. 5. Oh, there's 10.
AD is 5. AB must be congruent to this. That's 5. Therefore, BD has got to have a length of 10. Similarly, I know that I have a diameter. It's bisecting this chord. A diameter, it's perpendicular to the chord, therefore it's bisected. Therefore, each of these two chunks must be equal to each other. Or 3x plus 16, it's got to be the same as 12x plus 7. 9x is equal to 9, x is 1. Here's an interesting one. What's the measure of arc MN? Well, how can we reason this? Well, if I know that arc LP is 61, if I know arc LP is 61, well, I know this chord is bisected. This is a perpendicular bisector, so if I can look at this central angle here. And if this chord is bisected, that means that each of these points is equidistant to the center. Therefore, this is not only a perpendicular bisector; it's also an angle bisector of angle MQP. Which means if LP is 61, then LM must be also 61. Well, how am I going to use that 61 to find what MN is? I didn't care what ML is. Well,
Yeah, 61, 61,
okay, you could do that. You could say twice of MN, so MN plus NP plus 122 is 360, and solve. Sure, we could do that. I get your answer. Andrew, do you have alternate ways to do this? Since we know that NL is a diameter, because it's going through the center, NL must be a diameter, which means that LN is a semicircle, which means that this semicircle here is 180 degrees. So if you knew this was 61, you could alternatively do 180 minus 61, would give you the exact same answer that you got, Val, which should be, in this case, what, 119? Absolutely. Last but not least, for today, is our last idea about chords, is the chord, we're going to say the chord distance theorem. It says that in a circle, or congruent circles, two chords are congruent. Two chords are congruent if and only if they are equidistant from the center. How do we measure the distance from a point to a line segment? Can you just pick anything at random and just start measuring? How do you measure the distance from a point to a line or a line segment? Can we just do it in any way? We just take a ruler and put it however we feel and just kind of pick a distance? The answer is no. That's where that question was needed. How do you measure? No, nothing to do. If I give you, side note, should go over here. If I give you a point and I give you a line, how do you measure the distance from this point to this line? Do I just draw whatever line I feel? No.
Perpendicular.
I have to draw it at a perpendicular distance. This would not measure the distance. So if I measure the distance, I'm always measuring at a right angle. So at a distance measured by the segment from the center to that chord at a right angle, these distances must be congruent. Those distances must be congruent. Those must be equidistant. Those distances must be congruent if the chords are congruent. And vice versa. If those distances are congruent, then you know the chords are congruent. Or, if you know the chords are congruent, then you know those distances are congruent. That's the if and only if part. So, as some of the examples below, in this case, I have one circle, and I'm telling you that these two chords, if I measure at a perpendicular distance, are both 18 units away from the center. Knowing that they're both 18 units from the center, what can you conclude from this theorem? That the chords themselves are congruent. Since they're equidistant from the center, these chords are congruent. So then what could we do to find the variable? Set that distance equal to this distance and find x. Okay. If you know, in this case I'll just mark it congruent. So similarly, you know that the chord lengths are congruent. You can do this one on your own. The last one says find the arc measure of TU. Boy, oh boy, now we're going to have to throw together we're going to throw together a couple of the theorems we had today. So let's see. By the previous theorem, I know that since these chords are equidistant from the center, that the chords themselves are congruent. If you have congruent chords, what do you know about the arc, the minor arcs that they create? They are also congruent. That was from like our first theorem. That was from our first theorem. So combining the last theorem, knowing that the chords are equidistant, and also knowing that the chords are congruent, we know that the minor arcs they create are also congruent. So therefore, we could claim vis-a-vis, we could claim that arc TU is got to be the same as measure arc SR. Therefore, measure of arc TU is equal to 95 degrees.